Assalamu alaikum. Dear learners, I hope you are fine and doing great. Today I am going to take you through the forward kinematics of a very famous 7 degree of freedom Cobot Kuka iiwa. It is a lightweight robot from Kuka and comes in two different versions. One of them is iiwa-7, which has a payload capacity of 7 kg, while the other is iiwa-14, having payload capacity of 14 kg. I'm going to solve forward kinematics of iiwa-14 and then will use MATLAB SimScape toolbox to validate my working. Moreover, MATLAB has this robot's URDF built in, so we will be able to visualize it as well. Before I start to solve the forward kinematics, what are forward kinematics? Forward kinematics, put in very simple and straightforward words, is that we are going to provide joint angles to the robot and the robot is going to move. Now, forward kinematics will tell us that where the end effector of our robot is, that is, what is its position and its orientation. So for forward kinematics, the input is the angles. As in our case, we have a 7 degree of freedom robot, so it will have 7 different joints. So all the joints will have some theta associated with them. So we are going to have theta 1 till theta 7. When we will provide these joint angles to the actuators will move and hence the robot will move. Over here, the forward kinematics will tell us that if you supply these joint angles to the robot, where your end effector will be. And the position and orientation of the end effector will be in form of a homogeneous transformation matrix. A homogeneous transformation matrix is a 4x4 matrix in which this 3x3 portion represents the orientation of the end effector, whereas this 3x1 vector represents the position of the end effector. You're always going to have 3 zeros and a 1 as the last row. To ease out everything in formulation of forward kinematics, there are different conventions being used all around the world. But the most famous one is the Denavit-Hartenberg convention called the DH convention. We know that we are living in a 3D world and we have 3 independent axes. Therefore, we can have 6 independent movements if we want to go from one position to any other position. Those 6 independent movements are the movement or translation in x-axis, translation in y-axis, and translation in z-axis. Apart from these translations, we can rotate about x-axis, rotate about y-axis, and rotate about z-axis as well. So in total, we have 6 independent movements. But the DH convention says that we can move from one frame to any other frame or any other position using only 4 basic movements. That is, out of 6, we can use 4 of them and move from one position to another position. But for this to be true, we have to make sure that the frames through which we are moving, they are not displaced in y, that is, they have no movement in y-axis, and they have no rotation about y-axis. So if we have omitted translation and rotation about y-axis, then of course we will be left with 4 basic movements. That is, translation in x and z-axis, and rotation about x and z-axis. Now, to make sure that the frames which we have assigned to our robot are in compliance with the DH convention, there is a very simple rule. And that rule is that make sure that the x-axis of the current frame, that is the frame you are assigning, is intersecting and is perpendicular to the previous z-axis. If you can somehow make this sure, then we are confident that we haven't moved in y-axis and we haven't rotated about y-axis. So this is the only point you should be considering while assigning the frames. So let us use this convention to formulate the forward kinematics of the robot which I have shown you. So here is this robot and I have labeled the dimensions of this as well. So what we are going to do is we are going to provide joint angles to this robot. So we are going to have 7 unknowns, that is 7 joint variables. Those joint variables are going to move this robot and we want to know where the end effector is going. To do this, we need to assign some frames to this robot. And then we have to move from frame to frame so that we can start from our reference world frame and go till the end effector's frame. I'm going to do that with you. But to store this information, that how we are going to move from one frame to another frame, we have to use a table called a DH table. So this kind of DH table will be used. So I'll explain along the way that why I have formulated this table like this. So once we have this table will give us the homogeneous transformation matrix that will relate the world reference frame or our reference frame with the end effector's frame. And that homogeneous transformation matrix will give us the end effector's position and orientation. That is what we want. So the very first thing to start is we need to know where the joints are. So I'm going to overlay the joints over here. So these cylinders are showing you the joints which are present inside this robot. So we have this, I'm going to label over here. So we have this joint 1, then joint 2, and similarly I can label all others. So we have 7 joints from J1 to J7. Now the first thing is we need to figure out where the z-axis of all the frames are. And the easiest way is to assign the z-axis to be the actuation axis of the joints. So I can say that the actuation of joint number 1 is about this axis. So I'm going to label this axis as Z0. That is my first joint axis. After that, this joint J2 will have this joint axis. So I'm going to label it as Z1. And for the third joint, this will be the joint axis. So I'm going to label it as Z2. Over here, this will be the joint axis for joint 4. It will be labeled as Z3. Similarly, joint 5 will have this joint axis. So it will be labeled as Z4. Then I'll have this joint axis for joint number 6. It will be labeled as Z5. And then for joint 7, it will be this one. It will be labeled as Z6. And at the end, we can have the end effector at some higher point. And this thing will be labeled as Z7. So we have all the z-axis. Right now we haven't defined any world reference frame. So you can either take this z0 or the frame 0 as the world reference frame, or you can define one on your own. So let us define a world reference frame over here. So its z-axis is this one. So I'm labeling it as maybe zw. So that's the first step. The second step is to define the x-axis. So once we have defined the x-axis of all these frames, we have defined all the frames completely. So to define you should already know that to define a frame, you need to define at least 2 axes of it. So we have ZW, Z0, Z1, and similarly up to Z7. But where are the x-axes? So we can define the x-axis. Maybe x-axis can come out of this point at where the origin of the world frame is, or it can go towards the right or towards the left. It can go anywhere. It's up to you. I'm going to choose this x-axis, which is coming out of the plane of this video. So I'm going to label this thing as XW. Now I have defined the world reference frame. Now for the next x-axis, which will be x0, I have to follow the convention laid down by Denavit-Hartenberg representation. So x0 can only be intersecting and perpendicular to the previous z-axis, which is zw. So x0 can come out of the plane of this video at this point, or maybe at this point, or maybe at this point, or any other point. So the most suitable point is this one, because we know the distance between the world frame and this point, which is given over here as 0.1575. So I'm going to choose this point. Moreover, over here, x0 can go into the plane or can come out of the plane of this video. It is recommended to choose x-axis similar to the previous x-axis if it is an option. So we have the option of choosing x-axis to be coming out of the plane or going into the plane. So I'm going to choose x-axis to be coming out of the plane because the previous x-axis, which is xw, is coming out of the plane. So this will be x0. So this defines frame 0, which is present over here. Now, for the next x1 axis should be perpendicular and intersecting with z0, that is the previous z-axis. So you can see that z-axis is intersecting with this z1 at this point. So this is the only option we can have for x1. We can make x1 go into the board or make it come out of the board. So once again, I'm going to choose x1 to be coming out of the board. So this is x1 for me. Now moving on to x2, we can see that the z-axis x2 should be intersecting and perpendicular to z1 this time. So we can see that z2 is intersecting with z1 at this point. So the only option we can have for x2 is once again this point. So x2 will be same as x1. So this axis is x2 and x1 as well. So I can extend this z2 axis till this point. So this is the frame. So this is frame number 2 and frame number 1 is over here as well. They are just rotated with respect to each other. So after this, we'll move on to frame number 3. So you can see that this z2 axis is intersecting z3 at this point. So we can have x-axis over here, and options can be going into the plane of this video or out of the plane. So once again, I'm going to choose x3 to be coming out of the plane. Now it's the same thing once again. So z4 is intersecting z3 at this point, and x4 can only be at this point. So once again, x4 can come out of the plane or go into the plane. So I'm choosing it to be coming out of the plane, similar to x3. I'm going to extend once again the z-axis. So once again, frame number 3 and frame number 4 are at the same point. The only difference is that they are rotated with respect to each other. Now coming towards x5. So z4 is intersecting x5 at this point. So once again, I have to choose x like this. So it will be x5. And for x6, z6 and z5 are intersecting at this point. So this axis will be x6. And for x7, as z6 and z7 are parallel and overlapping, so I can choose x7 to be anywhere. I'm going to choose a reasonable position, which is this one. So okay, once we have defined and assigned all the frames to this robot, the other thing is we need to figure out what are these parameters to fill in this DH table. I said that we can go from one frame to another frame by doing 2 translations and 2 rotations. So over here, this A is nothing but translation in X. So I can label it as translation in X. Whereas this alpha is nothing but rotation in X. This D is nothing but translation in Z, and this theta is nothing but rotation in Z. So we have to now figure out what are these 4 parameters for every transition we are going to make. So the very first transition, that is, we need to come to link number 0 or frame number 0, you can say. We will start from world frame and we will come to this frame number 0. So what are these 4 parameters or transitions that we need to come to frame number 0? So do we need to translate in x-axis? No, we don't, because x-axis is coming out of the board. We don't need to come out of the board. So this A is going to be 0. Do we need to rotate about x-axis? No, we don't, because z-axis, if we'll rotate about x-axis, the z-axis of these 2 frames will not be pointing in the same direction. Right now, zw and z0 both are pointing in the same direction, so it means we are not rotating about x-axis. So once again, this alpha is going to be 0. So after this, what is the translation in z-axis? So if we are at this point, this is our starting point, and we have to translate by 0.1575 units in z-axis so that we can reach this point. So over here, I can write 0.1575. And do we need some rotation about z-axis? So as this world frame is fixed, it cannot rotate. So you cannot rotate about z-axis. So you cannot rotate about this zw. So right now there is no rotation. Both x-axes are pointing out of the plane and they are parallel. So there is no rotation between them. So this theta is going to be 0. So this is the first row of the DH table. Now the second row, we need to move from frame number 0 to frame number 1. And do we need movement in x-axis? Of course not, because we are not coming out of the plane of this video. Do we need any rotation about x-axis? Yes, because over here, z0 is pointing upwards, whereas z1 is pointing towards the right. So you have to rotate by minus 90 degrees to make z0 in the direction of z1. So over here, alpha is minus 90. Then to move from this point in the z direction, you have to move by 0.2025 units to come to this origin. So over here, it will be 0.2025. And is there any angle between x0 and x1? That is, have you rotated about z-axis, z0? Then right now at this configuration, we haven't rotated. But what if we actuate joint number 1? When we'll actuate joint number 1, everything after joint number 1 is going to rotate. So link 1 is going to rotate, frame 1 is going to rotate, frame 2 is going to rotate, and everything is going to rotate. So if frame 1 is going to rotate, then the x-axis, which is x1 axis coming out of the plane of this video, will rotate about the z0 axis. So there will be some angle between x0 and x1. So we are going to label it as theta 1. So this means that this theta 1 is a variable, and it will depend that how much actuation we have given to joint number 1. Now using the same formulation, we can come from frame number 1 to frame number 2. So as both origins are at the same point, frame number 2 and frame number 1, they have origin at the same point. So it means we haven't translated in any direction. So I am directly going to write zeros over here because there are no translations. And if we see over here, the z-axis z1 is pointing towards right, whereas z2 is pointing upwards. So it means we have rotated about x-axis, and you have to rotate by 90 degrees, positive 90 degrees, so that you can make z1 come in the direction of z2. And once again, x1 and x2 are pointing in the same direction, but when you will rotate joint number 2, x1 will not move. Only joint 2 and everything after that will rotate. So frame number 2 is going to rotate, frame number 3 is going to rotate, and everything after that is going to rotate. So x1 will still be pointing outwards, whereas x2 will start moving. So there will be some angle between x1 and x2. So that angle can be denoted by theta 2. Same formulation can be followed, and I can quickly write that there is no translation in x-axis, so all a's are going to be 0, and then there is going to be 90-degree rotation over here when we are moving from frame 2 to frame 3. Then from frame 3 to frame 4 we are going to have minus 90-degree rotation. Then from frame 4 to frame 5 we are again going to have minus 90. From frame 5 to frame 6 we are going to have plus 90. And from frame 6 to frame 7, there will not be any rotation. As for translations, we are going to have 0.42 units translation in z-axis when we are moving from frame 2 to frame 3. Frame 2 is over here and frame 3 is at this point. So this is the movement that we are going to make. So it is equal to 0.42. Then for moving from frame 3 to frame 4, we don't need any movement because both frames are at the same point. Then from frame 4 to frame 5, we'll once again use this movement. So this will be 0.4 this time. You can add these two values up. And for moving from frame 5 to frame 6, we don't have to move, so it will be 0. And then from frame 6 to frame 7, we have to move this much. It is equals to 0.126. And all the joint variables which are associated with these joints are theta 3, theta 4, theta 5, theta 6, and theta 7. So this is the DH table which we have formulated. First four elements, that is the first row, can be used to figure out the transformation between world frame and the frame 0. Then second row can be used to figure out the transformation between frame 0 and frame 1, and similarly we can figure out transformations between all the frames. If we multiply these transformations up, we will end up with a combined transformation from world frame to frame number 7, and that is what we want. Our end effector is present at frame number 7, our reference is the world frame, and we want to know where the end effector is with respect to the world frame. So let us move to the MATLAB environment and try to code this DH table so that it will automatically figure out what is the homogeneous transformation matrix between the world frame and the last frame, that is the end effector's frame. So before coding the DH table over here, we need to have the Kuka iiwa14 robot over here. For that, I said earlier that this robot is already built into MATLAB, You can load its URDF by writing this command. Over here, import robot function will import the URDF of this robot into a variable named as robot. Once the command has executed, you can use another function named as smimport, provide it a variable which you have just created, that is robot variable. What this function will do, it will generate a SimScape multibody model of this robot so that you can visualize what the robot looks like, and if you want to move it in a 3D environment, then you can have that as well. So here is our robot. You can see that over here at the start, we have the world frame and the first link, that is the frame 0. After this, we have a joint which is labeled as joint 1. Then we have link 1, then joint 2, link 2, joint 3, and similarly we have up to joint number 7. So the joints from joint number 1 to joint number 7 are revolute joints. Whereas at the end, we have these fixed joints and we have some frames for the end effector, because right now there is no end effector attached, so there is nothing over here. Just to make sure that you have imported the right thing, you can import this thing and just click on run. Once compiled and executed, and if you have done everything right, you will see this robot like this in the Mechanics Explorer. Over here, you can see all the links and then all the joints and everything over here. And in this panel, you can see the robot. You can change its view to view different sides of this robot. And you can also visualize where different frames are. For example, if you click on this world, then world frame will be highlighted. So world frame is right at the base. If you view the front view of this robot, you will see that it is exactly at the base. I have used the right view of this robot to place all the joints and then use it to figure out the DH table. So we placed the world frame over here. Then the next joint was over here, which was joint number 1. Then it was joint number 2, then 3, 4, 5, 6, and 7. And at the end, we have the end effector. These frames are a bit different than what we have assigned because these are the CAD models frame. So these frames has nothing to do what formulation we have made over there. So once you're sure that this is the robot and you have loaded it perfectly, now we should come back to our Simulink model, and we need to actuate this robot so that we can move it. We need to provide some angles to joints, and we need to sense those joints as well. So to provide some angles to these joints, you have to double click on the individual joints, and then in the actuation portion you have to click on, for the motion you have to select provided by input, and for torque you have to select automatically computed. And for the sensing portion, that is you want to sense what the joint angle is, you can click on this sensing position. You have to do this for all the revolute joints. So you have 7 joints, you have to do it 7 times. So once done, you have to provide joint angles to these 7 joints. For that, you have to generate some Simulink signal. And for that, the first thing you need is a Simulink to PS converter. So you can double click anywhere, type in Simulink, and select Simulink to PS converter. Double click on this Simulink to PS converter and select input signal unit as radians, because we have attached a revolute joint, so it will need some input in the form of radians. And for input handling, because MATLAB needs to calculate the torque automatically, we need to provide derivatives as well. So you need to select filter input, derivatives calculated, and you need to do the second order filtering. That's it. We need 7 of these converters because we need to provide signal to all 7 joints. Now you should connect these converters to these joints so that whatever signal we provide to these converters, that will be converted into physical signal of this SimScape Multibody module and provided to the joints. Same thing has to be done for sensing these joint positions. So we now need PS to Simulink converters because we will be getting some signals from the joints, and as we have 7 joints, we will be needing 7 PS to Simulink converters. We have to connect these converters to these sensing ports so that joint position sensed by this block will be converted to Simulink signal and given to us as output. That's it. Now we can enclose everything over here into a subsystem. So you can select it, right click anywhere, and click on this create subsystem from selection. So this is our robot. It has 7 inputs and 7 outputs. You can label it as robot. Now we need to provide 7 joint angles to this robot. This robot will move, then it will figure out the joint angles, sense those joint angles, and will give us the output. So to provide joint angles over here, I'm going to be very simple because we need to test the forward kinematics which we have formulated. So over here, I'm going to use a constant. This constant is going to provide an array of 7 values. So by default, I'm going to use 7 zeros. I have to convert these values into radians so that I can easily provide values in degrees. And then I have to demux them into 7 different values. I'm using a demux of 7 outputs. I'm just going to connect this demux to the 7 inputs. So I'm going to supply joint angles at this position. They will be converted into radians and then they will be provided to the robot. The robot will move and I will sense those angles over here. These angles should be given to the forward kinematics algorithm. Forward kinematics algorithm should use those angles and should give me the homogeneous transformation matrix relating the world frame with the end effector. From that homogeneous transformation matrix, I can figure out the rotation of the end effector and the position of the end effector. So over here, I need to make a function file that will take in the 7 theta values and will give me the homogeneous transformation matrix. For defining the function file, you can come over here in the Simulink library. Under this user defined functions, you can come over here and select this block, which is MATLAB function. Drag it over here. And right now you can see that there is one input to this function and one output. We can define our forward kinematics algorithm in this block. So if you double click it, a function file will open and you can type in the function over here. So over here, the output would be H, that is the homogeneous transformation matrix. And I'm going to name this function as forward kinematics. And there are going to be 7 inputs from theta 1 to theta 7. The very first thing over here I need to do is I need to define the DH table. And for DH table, there are 4 different things. The first thing is the A. The DH table which we had 8 rows in that, which means all 8 A's were zeros. So I'm going to have 8 zeros. That's it. These are my A's. Then the second column was alphas. So first alpha was 0. Second one was 90, minus 90, sorry. Then 90, 90 again, minus 90, minus 90 again, 90, and the last one was 0. So these are my alphas. After this, there was the D column. And for D, I have these things. And the last one was theta. The first one was 0, and then we had 7 thetas, from theta 1 to theta. Now I'm going to use first value of each variable to figure out the first homogeneous transformation matrix that will take me from the world frame to the frame 0. Then the second value from each variable to figure out homogeneous transformation matrix that will take me from frame number 0 to frame number 1, and similarly from 1 to 2, 2 to 3, and at the end from frame number 6 to frame number 7. For this, I have to write a for loop that will automatically take the values and will figure out the homogeneous transformation matrix. So this is what I have written. I have initiated an intermediate matrix A, which will be initially zeros, and it will have dimensions of 4 by 4 by length of A. So all the homogeneous transformation matrices are going to be saved over here. So I'm going to have 8 homogeneous transformation matrices. Then to combine all 8 homogeneous transformation matrices into one final transformation matrix, I have this H variable. So over here you can see that I have written this big matrix that has 4 rows and 4 columns. The last row is 0, 0, 0, and 1, whereas the other 3 rows have some values. Over here I am supplying theta value. I have used a different variable name over here, so let me change this one to th because I have used th over here, and I have used al for alpha, so I'm going to change this alpha to al. So I'm going to supply 4 values to this big matrix. I'm going to supply theta over here, alpha over here, and in many other places as well, a over here, and D over here. So these four values in the first loop will come as the first values from these matrices. So I'm going to supply these four values and I'm going to get the first homogeneous transformation matrix in the first loop, second homogeneous transformation matrix in the second loop, and similarly I'm going to get 8 homogeneous transformation matrices. All those 8 homogeneous transformation matrices will be multiplied with each other and I'm going to get a final homogeneous transformation matrix H. I need to convert these thetas into degrees so that I can use them with this cos d function and sin d function. So I should convert this vector into degrees. So I can use a function radian to degrees over here, and it should do the job. And now over here you can see that this block has changed. Now it has 7 inputs. The name is Forward Kinematics, and there is one output. To visualize this output, I have to connect these outputs to this thing. That's it. Now to display this homogeneous transformation matrix, I can use a sync display. So that's it. This is my algorithm. Now I'm going to provide some joint angles, convert those to radians. Those radians will be provided to our robot. The robot will move, and the forward kinematics will use the angles onto which robot has moved, use those angles to figure out what's the homogeneous transformation matrix, and that homogeneous transformation matrix is going to tell us where the end effector is and what is its orientation. So let me run it. Right now I'm providing all zeros to the robot, so the robot shouldn't move. So after running, this is the homogeneous transformation matrix I'm getting. You can see that in this 3 by 3 portion, I'm getting an identity matrix, which means the end effector frame is perfectly aligned with the world frame. And the end effector's position is 0 in x-axis, 0 in y-axis, and 1.306 in z-axis. So let us go to this Mechanics Explorer and we can see that the robot is standing tall. And if you explore this tree, the world frame is right at the bottom, z-axis is pointing upwards, y-axis is pointing towards the right, and x-axis is coming out of this plane. And if you see the end effector's axis, which is this one, z-axis is going upwards, similar to that of the world reference frame, y-axis is going towards the right, similar to that world reference frame, so x-axis is coming out. So that's why the rotation portion of the end of the homogeneous transformation matrix was showing an identity rotation. And you can see that the end effector is somewhere in the z-axis of this world reference frame. So from this origin, if we move in z-axis, we'll arrive at this end effector position over here. And from the homogeneous transformation matrix, we know that this distance is 1.306. Okay, let's try to move this robot to a new location. Let me change these joint angles. What if I give 90-degree rotation to the second joint? So I have changed theta 2 to 90 and everything else is 0. You should have in your mind that how the robot should move. So let me run it once again. Okay, so when we have rotated joint number 2 by 90 degrees, we have this rotation matrix and this translation vector. So if we come over here and view this thing, we can see that the robot has rotated from this joint, which is joint number 2. Its z-axis in this direction, so it has rotated by 90 degrees. First it was standing tall, high, vertically, but now it has become horizontal. So if this is the world frame somewhere over here, it has some displacement in x-axis. The end effector is now at this point, so it has this displacement in x-axis, some displacement in z-axis, and nothing in y-axis. So over here, if we come back, we have nothing in y, 0.946 in x, and 0.36 in z. Over here, you can see that the rotation matrix is this one, and the first column shows that the x-axis of the end effector is in the direction of z-axis of the world frame, but in the opposite direction. So let us see over there. So this is the end effector, and you can see that x-axis is coming downwards, whereas for the world frame, z-axis is going upwards. So x-axis of the end effector is perfectly aligned with z-axis of the world frame, but going in the opposite direction. That's why we are getting a -1. Then for y-axis, y-axis is perfectly aligned for both of the frames. Let us see that. So the world frame's y-axis is going inwards, and the y-axis of the end effector is also going inwards. And for the last axis, the z-axis is perfectly aligned with the x-axis of the world frame. So we are getting a 1 over here. So this is the z-axis of the end effector, and it is perfectly aligned with the x-axis of the end of the world frame. So dear learners, you can provide any angles over here in degrees. Those angles will be fed to the robot will move, and the forward kinematics will figure out that where your end effector is in terms of orientation and position. So this forward kinematics algorithm, which we have formulated by using the DH convention, is working perfectly for this robot. If you have any queries or don't understand or didn't understand anything, I'm always available through YouTube comments or my email. So feel free to contact me if there is any issue. Till the next time, take care and goodbye.